This question is about silver iodide, and it starts by asking us to define the term enthalpy of lattice formation. So lattice formation, and for silver iodide, is when we're trying to form the silver iodide lattice, which is the solid ionic crystal, and we're forming it not from elements but from ions, and those ions are in the gaseous state. So we need to write that in words. So the enthalpy change. Now if you wanted, you could explain what enthalpy change was here by saying the heat energy change. Then you need to say what of, and it's got to have a 1 mole in there. So when 1 mole of solid ionic lattice, in this case solid silver iodide, is formed, and what's it formed from? It's formed from its, so the ions it's got, and they need to be in the gaseous state, its gaseous ions. Then if we move down, we're being given some enthalpy change data, and we're being asked to calculate that enthalpy of lattice formation. So let's just rewrite that equation. Ag plus, state symbol's so important when you're dealing with enthalpy changes, because obviously changes of state take or release energy. This is our unknown, so I'm going to give that an X. Then I'm going to look at the table of data. The first thing I've got here has Ag solid, and Ag solid is placed right here. I can see that the arrow points away from Ag solid and goes to Ag plus Aq and I minus. That's the enthalpy of solution. That's plus 112 for that change. Then the next thing, I've got Ag plus gas here, and this is given to me there. And that arrow is minus 464. And then I have got value for I minus gas, which is here, going to I minus Aq, which we can see is also happening down this side. This is minus 293. So in total, this total of this side here, if we use our calculator, we can see that this side is minus 757. And according to Hess's law, enthalpy change is independent of root. So as long as I start at the same place and end at the same place but go a different route, then I can see that to get the short route, just x, is equal to follow the minus 757 and then go against the 112, so it becomes a minus 112. When you type that on your calculator, you should get minus 869. And it says, a calculation for the enthalpy of lattice formation of silver iodide based on the perfect ionic model. So remembering that that's when they're perfectly spherical. That one gives this smaller, so less than minus, less than in size, but not worrying about the sign, less than 869. So if we just remove the sign, less than 869. But our calculated, which is our kind of real value that takes into account the real behaviour of these ions, is 869. So smaller means that if it was truly ionic, there would be less attractions in the lattice. But this is telling us that our value is bigger, so there must be some more attractions in the lattice, or stronger attractions. What is causing that is that it's not truly spherical, so that small silver ion is distorting that large iodide ion, and it's giving us some covalent character. So the fact that our value is bigger, says that AGI has some, so it's bigger in magnitude. We're going to not worry about the sign. The sign means energy released. So AGI has some covalent character. And because that covalent character is giving it a bigger lattice enthalpy of formation, a bigger value, this covalent character gives extra strength to the forces holding the lattice together. The lattice is stronger, the value is bigger. And our last question is a reagent to identify iodide ions, I-, so we need to remember that that's silver nitrate. You could say acidified silver nitrate, and what we'd see is a yellow precipitate of silver iodide.